So this video, we're going to look at what happens when we put a strong acid or a weak acid or strong base or weak base in water. And so we're going to talk about the difference between a strong acid, a weak acid, a strong base, and a weak base when they're added to water. What kinds of reactions do we observe? Do we see equilibrium? Do we see predominantly one side being favored? So we consider that more of a one-way reaction. And we're going to look at this with these 4 different types of possible solutions. So first, let's talk about what we mean by like a strong acid, and then we'll compare that to a weak acid. So reminding us, an acid is something that donates an H+. So if we put an acid in water, maybe something like HCl, it is going to react with water, and as it does that, it's going to donate its proton to water to give us H3O+, and whatever is left over, in this case, Cl-. So what we notice here is that we consider writing a one-way arrow. Now, why do we write a one-way arrow? Because these acids are so strong that they undergo 100% ionization or 100% reaction. So we can think of, in this case, the right side of the reaction is so heavily favored that we can consider it to be nearly a one-way reaction where whatever amount of HCl we put in, all of that's going to react to give us H3O+ and Cl-. Now, what does this mean for us as we think about what does this solution look like? So if I were to, for example, add in maybe something like 10 molecules of HCl, what that means is I'm going to get 1, 2, 3, 4, 5, let's just call it 5 molecules of HCl. All of those are going to react, and we're also going to get 5 ions of Cl- present in this solution as well. So we notice that we do not see any molecular HCl. We don't see it like hydrogen bonded to chlorine here because it is such a strong acid that every single HCl molecule present is going to fully donate all of those protons to water. So what this means, if I had 5 molecules of HCl, I'm going to get 5 hydronium ions and 5 chloride ions. Again, kind of going back to our original reaction. And again, we think of this as being a, per se, one-way reaction. Now, how does this relate to the pH of this solution? Again, reminding us pH is the negative log of the hydronium concentration. So if we get this kind of 100% reaction, that would mean whatever concentration of HCl I have, all of that reacts to give us H3O+. So here in this case, the concentration of HCl that we added or made the solution with is going to be equivalent to our hydronium concentration. So for example, if I have a concentration of HCl of 0.1 molarity, what we'll notice is that that would mean I have a concentration of H3O+ of 0.1 molarity. All of that has reacted, and so therefore, when we look at this solution, we notice that all of the HCl has now become H3O+. And so our pH would be the negative log of 0.1 or 1.00. And that would be the pH of our solution here when we're looking at this strong acid. And again, thinking about this idea of 100% reaction. Now maybe let's compare that to a weak acid. So weak acid here only undergoes partial ionization. So now here we're going to look at HF. HF is a weak acid. So we have HF. It's going to react with water. And when it does so, because it only partially reacts, what we'll notice is that that's going to mean we'll still have some HF left in solution, but then some of that is also going to react with water to give us the hydronium ion and the anion with it, which in this case is the fluoride ion. And so again, if we think that we add in maybe something like 5 molecules of HF, what we'll notice is that we have, of those 5, maybe 4 of them and this is exaggerated, actually be maybe if we had 5,000 and we have one of them actually ionizing here. But only a portion of that is going to give us a reaction where we get F minus, and then we also get an H3O plus. So what we notice here very specifically about a weak acid is that the majority of our weak acid are in this molecular form, right? It's hydrogen bonded to fluorine still. And so that's why we write this out as a double way or equilibrium reaction, because it's only partially reacted. Only a small percent of those hydrogen fluoride molecules are going to react with water and give us H3O plus and F minus. So what is the consequence of this for pH? That means that the concentration of H3O plus at equilibrium is not equal to the concentration of HF, because not every single HF molecule reacts with water to give us H3O plus and F minus. And so what that means is we need to think about how does this equilibrium constant, right? If we think of the Ka value specifically for this reaction, how does the equilibrium constant tell us about our original concentration and how it changes to how much of each of these are formed? And again, reminding us that when we talk about a Ka value, that Ka value is the acid ionization constant when we're looking at an equilibrium for an acid reactant. Again, weak acid undergoes this partial reaction, so therefore we only get a small amount of the solution that is actually reacting, and we have a majority of the molecule left over, a majority of this HF. And again, that Ka value will tell us how much of that actually reacts, if we have a small amount or if we have a really, really, really small amount. Okay, so that's comparing our strong acids and our weak acids. Now let's go ahead and look at our strong bases and our weak bases. And we're doing this in hopes of understanding what do the solutions look like, but also how do we write these reaction out in water. So here we have a strong base, sodium hydroxide. What we'll notice about all of our strong bases is that they are soluble metal hydroxides. So what we'll notice, because they're soluble, they are going to dissolve. And because they are a metal hydroxide, they are an ionic compound that is then going to dissociate. So if it's not soluble, it won't dissolve. And if it doesn't have hydroxide in there, it's not going to dissociate in this ionic compound to give us more hydroxide ions. So with our strong bases, what we'll notice is that these reactions are going to look a little bit different than our weak bases, strong acids, and weak acids. So what we'll see here is that we'll have our sodium hydroxide, or our strong soluble metal hydroxide. It is going to dissociate, and I'm just going to write water above this to say we know that this is in water. When it's in water, it's going to give us sodium ions and hydroxide ions. And so in this case, we notice that this is a one-way reaction, and that is again because we get 100% dissociation. So again, we have this ionic compound that contains these two ions, and they are dissociating or breaking apart into the two ions that they were originally. So that would mean if I had 5 formula units of sodium hydroxide, I'm going to get full dissociation. So I'm going to get all of these sodium ions are going to dissolve, they're all going to dissociate, and they're all going to give us a 1-to-1 ratio of our hydroxide ions and our sodium ions. Again, that's because we have a 1-to-1 ratio here. So again, we have this full 100% dissociation, so that's why we have this one-way reaction arrow instead of writing this two-way reaction arrow. Now, how does this relate to pH when we're thinking about calculating pH? What we would think about, again, if we have pH, we need to know either our hydronium ion concentration or our hydroxide ion concentration. We have to know one of those because we know that those are connected, and maybe we'll look and see, well, what is being produced in this reaction? We notice that we have hydroxide being produced in this reaction, so that's going to maybe tell us something about the hydroxide ion concentration. And so what we'll notice here when we're looking at this, we need to figure out what is the concentration of from the full dissociation of the whatever strong base that we have here. So the full dissociation of our strong base. So we can't always say per se the concentration of our sodium hydroxide or our calcium hydroxide or our strong base is equal to the hydroxide, because we got to look at what is the stoichiometry. So for example, if my concentration of sodium hydroxide is 0.1 molarity, that would mean, because it's a one-to-one dissociation, I'm going to have a concentration of hydroxide of 0.1 molarity. Now let's say we have calcium hydroxide is 0.1 molarity. Now what we notice here is that every single calcium hydroxide gives us 2 hydroxides. And so our hydroxide concentration is going to be actually double that, or 0.2 molarity. And that is a consequence of the fact that for every 1 mole of calcium hydroxide, we have 2 moles of hydroxide. So we got to pay attention to the stoichiometry of our salt that's going to be, or ionic compound that's going to be dissolved here. Now then, how does that relate back to pH? Again, now once we know our hydroxide, what we could do is we could use that to find our hydronium concentration, and we could use our Kw relationship. So the product of our hydroxide and hydronium equals Kw, and then we can go back to pH using pH equals negative log of our hydronium concentration. So notice we have an extra step that we got to do here. Or if we wanted to, we also have the ability to calculate pOH. And if we think about pOH and what pOH is the negative log of the hydroxide concentration. And then from there, we can calculate the pH, because we know the sum of our pOH and pH is 14. So again, we kind of take an extra step along the way, but again, focusing on the fact we know that a strong base undergoes 100% dissociation and includes the hydroxide ion in its ionic compound. Now let's go to our last possibility, which is a weak base. A weak base is something that undergoes partial ionization. So again, now we're thinking about this ionization reaction, reacting with water to produce these new ions. But again, they undergo a partial reaction. So let's look at our example here. We have NH3. It's going to react with water. Again, this is our ionization reaction. They got to react together and allow proton to be transferred to ammonia. Ammonia has to accept that proton, which is why I consider it to be a base. And then we go ahead and write our double way arrow here again, because we have this partial reaction or partial ionization. And we're going to get NH4 plus and hydroxide, because we've now stolen that H plus away from the water molecule. So what does that mean when we look at our solution over here? Let's say we have 5 NH3 molecules. We're going to end up with the majority of these still being NH3. So maybe let's just say 4 out of the 5. And again, this is a slight exaggeration because it's probably maybe 4 out of 5,000. Very small amount that actually gets ionized. But again, we're just kind of conceptualizing it here. And then we'll get one that is NH4 plus, and when it did that, it created a hydroxide ion, right? Because we see that that's the reaction that's happening here. It's reacting with water, and again, we're not necessarily noting that that's all full of water molecules. We have an excess of water molecules here. So now, what does this mean for us as we're thinking about our pH and how this relates to our reactions? Again, we have a partial reaction, so we think of an equilibrium reaction. So we're looking at the equilibrium here. Now the K value for this is our Kb. So that would be the Kc for the base ionization reaction. And so our base ionization reaction here, we have a base reacting with water. It's undergoing this base ionization reaction. This would be equal to NH4 plus OH minus divided by our NH3 concentration. So now we have the ability to relate our equilibrium constant to the concentration of ammonium and hydroxide that we'd have be forming here in our reaction relative back to the original one. So again, we cannot make the conclusion. What we note here is that the concentration of NH3 that we initially add into our solution does not equal the concentration of hydroxide. Again, that is because we are dealing with a partial reaction. So what we'll have to do is think about this. I'm going to have a follow-up video to this that actually works through some examples of these. But again, we look at the fact that we have an equilibrium. So we're going to set up a Rice table and kind of follow the process of thinking about what is our equilibrium concentration of hydroxide to be able to actually identify how much we have at equilibrium. So hopefully this gives us a good idea of what our strong acids, weak acids, strong bases, and weak bases look like in solution and how we think about writing those equilibrium reactions.